All right, today we're going to learn about linear and nonlinear functions. Okay, make sure you are listening to this with your headphones on. You will hear a special word today. So how do we use a table or a graph to determine if a function is linear or nonlinear? Okay, so we're going to be looking at tables and we're going to be looking at graphs and figuring out whether it's linear or not linear. Here's some examples of each. On the left side here, I have forms of linear functions, right? So we've seen positive sloping lines, negative sloping lines, zero sloping lines, right? So all these are examples of linear functions. And remember, Friday we tried the vertical line test. If a vertical line crosses through it, you can consider it a function. Over here on the right-hand side, these orange lines, I have also functions, but these are non-linear functions. See this kind of U-looking shape, or this kind of like curve, or this one over here, or this one over here. All these are still considered functions because, again, if I draw my vertical line, it's still going to cross only at one point, and that makes it a function. So anyway, these are examples of linear and non-linear functions. Just to talk more about the vertical line test from Friday, again, see if I draw a vertical line on this first one, it's a function. So on the second one, but on this third one, no good, because if I draw a vertical line right on top of this red line, it crosses all over the place, so not a function. This one, it works fine, going up and down. Here, not a function. See if I draw a line here, or even here, or here, you can see it touches at two different points. This one is a function. This next one's not a function, and the last one's not a function. So I just want to show you the difference between a function and not a function. I'm going to use an example to illustrate this situation. So the table shows the height and distance a ball traveled that Jose kicked during a game. So during a soccer game, here it is. This is the time elapsing from 0 to half a second to 1 second to 1.5, 2, and 2.5 seconds. This is the height of the ball in yards, and this is the distance in the ball. What do you notice here in the numbers in the red box in the height? Do they all go up, or does it come back down? And the distance, does it all go up or does it come back down? Well, the answer to that can be found when we graph it. So is the rate of change constant for the height? Let's take a look. From 0 to 6.2 is increases by 6.2. Then it looks like it increases another 3.5. And then it increases by, I don't know, I think it looks like 5, 7, so that's going to be 0.8. And then it actually decreases, starts to go down. How much does it decrease by? Well, let's just subtract it with our calculator here to make sure. It decreases by 1.8. And then from 8.7 down to 4.2, it decreases by 4.5. So can we say that the rate of change is constant in height? We say no, it's not constant. All right, what about the blue one, the distance? Is the rate of change constant in distance? Well, let's take a look. It went from 0 to 13, that's up 13. From 13 to 26, that's up another 13. 26 to 39, another 13. And if I just continue this, it looks like, yes, it is constant. It continuously goes at the same rate. So it's a yes. The constant is 13 yards per half second. Every half second it goes 13 yards. So let's go to the next part. Let's go ahead and graph each situation. So if I plot each of these points, and remember I'm zooming back out here, I'm using these points here. This is my time. That's going to be my x-axis, my domain, right? And then the distance or the height is the range. It's the output here. So if I take a look, this one here in red represents the height in yards. So that looks about right. You kick a ball, it's going to go up in the air, and then it starts to come back down. If we graph the distance, let's zoom in here, check this out. If I just graph the distance continuously goes further and further away from where Jose kicked the ball. So that's a constant rate. So here, this is an example of a linear and nonlinear functions. Both of them are functions, both are correct, but we're actually graphing two different data points, two different scenarios, if you will. This one graphs the height of the ball versus this one, the distance of the ball. When the rate of change is not constant, we call these nonlinear functions. Okay, so just to let you know that. The keyword this week, by the way, is guitar. Guitar. All right, next, example number 1. Determine whether each table represents a linear or nonlinear function. Okay, so here we go. We're taking a look at some tables. We're going to figure out whether this is a linear or nonlinear function. So the first thing I do is, I'm given a table, I always try to find the pattern. So this first one, from 50 to 35, it dropped by 15. From 35 to 20, it dropped another 15. And from 20 to 5, it dropped another 15. On this side, it looks like it increased by 2. Increased by 2 and increased by 2. So I can find my rate of change is negative 15 over 2. And it continues to be the same each time. So check. This would be considered a linear function. Now if I jump over to my next one, it went up by 16, and then from 49 to 16, it looks like it goes up by 33, and then from 49 to 100, it goes up by 51. Now that, even though these are different, that might not necessarily mean anything. Let's double check over here. This went up by 3, this went up by 3, that's a problem, and this went up by 3. So the first time it was 16 over 3. The next time was 33 over 3, and these aren't the same. The next one was 51 over 3, also not the same. They're not equivalent fractions. So we would consider this a non-linear function. And so you'll see that today in your classwork and homework. Here's my last example. Which of these graphs are linear? And so you saw the video earlier today, or the example earlier in the notes. Which ones are linear? When I'm taking a look at this, the only one that's linear to me is this one here. All of them are functions. If I use a vertical line test, it only crosses the line at one point, right? All this at one point. Maybe this one's kind of drawn weird. It looks like it would only cross once, but all these are functions, but only one of them is linear. These are considered non-linear functions. Okay, so just to let you know. All right, that's it for the notes today.